If you have any questions, please come forward, or you can write on the chat. Emil?
I see.
Emil, we don't hear you.
You cannot hear me?
No, now we can.
No.
Thank you very much for the very interesting talk. And I like very much the presentation of the data of the simulation in terms of the energy stored, which is the kinetic energy of the mass, or plus the energy stored in the strings.
Exactly.
Now I am wondering how one will measure all these things to validate these simulations.
You were right. That's a challenge. You're right. We are planning to measure through acoustic technique, through optical techniques, the motion, but I have not been thinking to this issue so far, which I think could be done through different techniques, but I'm not sure I can answer your question. I think it will be tough. But the most difficult part, I think, is to build systems that are really tensegrity. I think that's the most difficult challenge, the most difficult part. So far,
Yes,
I have seen studies on tensegrity inspired systems, but not real tensegrity, because when you go to a small scale system, it is very difficult to build hinged connections. So there will be, if you don't build the system correctly, there will be a lot of bending. So the behavior will be that of with different general lattice.
Yes, it's. Are there strings which change their optical properties as you stretch them?
Yeah. Yes, there are this in this projection multi-stereolithography effect. There are this you can activate the members through different techniques. One is light, temperature, humidity, and you can use those effects to induce pre-stress. By altering the environmental conditions, you can induce pre-stress. But we have been trying that. But the problem was that these systems either were too stiff or too weak. So because of so we still have to balance to find the right technique, the right materials, for producing systems that have a very realistic tensorial response with only tensile, with only axial forces, only tensile and compressive force. So this is a basic ingredient of tensegrity. You know that otherwise it's a lattice. One basic ingredient of tensegrity is that you have only tensile and compressive forces. And so this has been very difficult. Obviously, when you build a large scale system, is easy. It's pretty easy. You can do that using strings, for example, using cables which do not carry bending moments. But when you go to small scale system, it's more difficult.
Yeah, yeah, my question was more into measuring rather than actuating.
I know, but
for example, in a plastic, in a transparent plastic, if you put particulates like in a liquid crystal, and then as you stretch, these particulates will change their orientation. by just shining a light on it, you should be able to detect a stretching of the wire.
I had this idea, but I'm not an expert of this experimental mechanics, so that's why I didn't brave to give you that answer, because I was not sure. Yeah, I think that optical methods can help. I know that, for example, to investigate on this acoustic lenses, you can build these systems in you can immerse the systems in water, and with the microphones you can measure the focal point of the waves introduced in this in a water environment. But this is about the wave focusing property. About the energy transported by the system, I would be very glad to collaborate with someone. If we build the right system, yes, I will look for collaborations about the possibility to expect about this. I think will be a very interesting research, investigating on the distribution of the energy to the systems. Yes, I think is a. I have been reading about methods for measuring the motion, for looking at the optical methods for investigating on the motion. But yes, that's a very important feature too.
Thank you very much.
Thank you for the interesting questions. Actually, you opened it, yeah. We were thinking about possible collaboration. This could be a collaboration, because I am not an expert of experimental mechanics. I am doing my best to learn about moving from a more background on simulation and computation towards experimentation, which is really necessary to prove the effectiveness of these systems. And I will be happy to learn about. Maybe we can start with the smaller scale systems in order to choose to find the most appropriate way of measuring energies. Maybe also with the thermal maps, measuring the temperature, maybe.
Yeah, that could be.
Okay, thank you, Emil. Is there any other question?
Yes, one point I would like to stress is that if I can, is that this talk has been focused on this novel use of tensegrity structures for acoustic applications, for acoustic purposes. This is theoretically, tensegrity structures are very appropriate, are very useful in this field, because you can effectively control the speed of sound. So you can control the speed of sound in the system by tensioning the springs. And this, you don't need to change the geometry. The geometry can be the same. You just slightly change, since the stiffness would be 0 in the initial configuration. You just induce stiffness through the pre-stress. You can dramatically change the speed of sound in the system. But the main challenge is building devices that are confined in space. So with the small scale units, the behaviors we have observed are scalable. So you can obtain those behaviors at every scale. But the challenge is to build systems at a small scale.
Could I ask a question?
Sure, please.
Very interesting movies, but since they are simulations, I was wondering why sometimes you could see things looking a bit like noise on the movies. Is that because of the accuracy of the simulation itself, or,
No, I
why
think
is there noise on some of the movies? You could see some rogue vibrations spreading out. They seem to be breaking the symmetry. I was just wondering how that happened.
the breaking of the symmetry arises from the chiral aspect of all the structures that we have examined. So they are not perfectly symmetric over the thickness. So there is this chirality induces some oscillations of the distribution of the energy of at the wave front. Maybe this is one source of oscillations in the movies. But one also another reason for those oscillations could be the thermalization of the system. So this is a pretty new result that we have observed. So there's a combination of thermalization and localization is something that is new in this area of research. Mostly mathematical research is only focused on solitary waves, while we observe this thermalization that probably affects due to the finiteness of the system. So probably if you study infinite systems, this will disappear. But the infinite system and these oscillations are present. Most probably are induced by this thermalization, the thermalization of the lattice.
Thank you. I think I missed the beginning of the talk, but I didn't see any experimental movies of the waves. Only an experiment.
And we have one experiment that I have shown. We have only one experiment run so far, and but I haven't shown it because it's on one 1D system. I don't know. I don't think I have the time now to find it. I can send it to you if you. You are Oliver. Are you?
Yeah.
Oliver, I will send you this movie. I will send you this movie. We ran this experiment in collaboration with Chiara D'Araio at the ATH some time ago, and we observed a partial validation of the theory because there was bending in the end. There was some bending in the system, so which linearized the response of the system. So there was some nonlinearity, but also some linearization of the response due to the bending stresses. But we have some experiments in there, and there are other experiments run by Chiara D'Araio, who is an experimentalist, who has continued this research. But the point is that these subsequent experiments showed also the presence of bending, and other experiments have been run on bistable structures, and the stability has been used for propulsion of tensegrity landers, but this is a different area of research.
Oh, okay. That would be very interesting. Okay.
I'll give you some material about experimental analysis, which is pretty limited in number.
Thank you. You can find my email on the web. It's up there. So thank you.
Okay, I will.
Okay, grazie. Yeah.
You are very welcome. Where are you from? Which university are you on?
I'm at Hokkaido University at the moment. Yeah, Hokkaido.
Okay.
Yeah.
Nice.
Okay, yeah. Thank you. Yeah.
Thank you, Oliver. Any other question?
I could go in again.
Yes, Emil,
I
please.
think at a slide where you present first time the 2D systems, if you can put that slide.
Yes.
It's interesting because so it is the slide with the squares like this. It's the schematic.
You mean the schematic of the stiffening response, or the first beam impacted?
Now, the very first slide, when you make the transition from 1D to 2D, there is this one, for example.
This one?
That's right.
Okay.
No, the one with the system itself.
This one.
The slide you show the slide where it's the first slide where you make the transition from 1D to 2D.
The bistable, probably. This one?
Maybe.
Because this is I'm not sure.
You already showed it was the 2 by maybe 10 lattices, 2 by 10 system.
Okay. So this was just a figure. This one.
This one, yes.
Okay.
Now here one observes that the bars don't rotate. How can that be?
No, this is so you have to so the bars. This is due to the loading condition. So it's basically they rotate as they can rotate as rigid bodies, and they are the mass is lamped at the nodes, and so those are like springs that attached to the nodes. So if they can rotate, yeah, they will rotate. They can rotate, as you can see in the animation.
Yes, but it was just on that slide where you chose to show them all parallel.
This is a particular snapshot. You can see some, for example, here you can see some rotation. You see at the very end.
Okay.
There is
So
a rotation in that member. Yes. This is just a snapshot. Most probably, yeah. In the initial part, you don't see much rotation. Yeah. But yeah, the member
yes, and the mass is like
you have not modeled as rigid bodies the bars, because we have assumed that the mass can be lamped at the nodes. But obviously, you can also model these bars as rigid bodies with rigid rotations, and yes, that's a refinement of the model that we look forward to implementing. And so far, in order to give more substance to this model, we assume that there are lamped masses at the nodes, so as to reproduce with the model the physical behavior.
There was the experiment where the system is fixed at one node, on one end, then you have the free end. I was wondering if you start oscillating the fixed end, and you do a map of as function of frequency and amplitude, one should see quite interesting. There will be transient behaviors, and then there should be some stationary behavior. So
yes, that's like a shock wave. But we were thinking of this application, the application of an acoustic lens. And that's why we wanted to create a device which was able to focus mechanical energy in a host medium. That's why we didn't focus on shock waves, or we focused on impact loading. But obviously, the response to more shock loading is different. You can have trains of compression waves interacting each other, and then at the given distance from the impact point, you can have a more smooth response. But
I was thinking about repeated, not like a shock wave, but rather a periodic in time, and look for the stationary.
Yeah, this has been done for granular materials, not for these systems. Yeah, this is a new area of research. Yeah, there are several things can be done. Yeah, this is one of the periodic loading is one of the there's a lot to do in this area.
Yeah.
Actually.
So for this, with this periodic loading, maybe one can understand better the excitations of this nonlinear system.
Yeah, that's true. That's true. That's true. Yeah, it is true.
Okay, so if there are no more questions, let's.
I've got one actually. I've got one, a very naive one.
Okay.
Can we go back to the solitary waves?
Yeah. The compression wave of the 1D or the 1D case?
1D case to start with.
Sure. Yeah, for example, here in this system, you have both compression and rarefaction waves. So in the first, you have this compact compression wave traveling there. This can be localized on 4 or 5 units or maybe less, depending on the phase speed of the traveling wave. If you are in the supersonic regime, the wave will localize on a single unit. And this is very useful in order to focus, to create localized mechanical waves. And interestingly, if you change the response to softening, instead, so you produce a rarefaction wave. So here, what propagates is a rarefaction wave. So this is a stiffening branch, this is a softening branch, the same geometry. You just pre-stress the fibers in a different way, the cables in a different way. And so this is what you obtain. So you obtain the propagation of, this is a softening branch. So with the axial stiffening decreasing with the amplitude of the displacement, that you obtain in this branch a rarefaction wave. So actually you decrease the initial precompression of the system. This is a negative behavior, negative response.
Can you control the phase shift at the reflection?
I think so. I'm not sure. I think so. Yeah. I think so. It depends on the, What you see is that these waves are supersonic. In this case of the rarefaction wave, you obtain that the tail is subsonic and the wave, the leading wave is supersonic. So in the rarefaction wave branch, this the wave front will separate from the tail, and so if the system is sufficiently long, only the rarefaction wave will survive, and this oscillatory tail will disappear. So these are very, very peculiar behaviors, which depends on the number of units. So you need a very large number of units to obtain this, to observe those behaviors. That's why that's the challenge for experimentation. Yeah, because you need to.
Typically, how many at least?
Yeah, you need at least 100 units so if you have one less than 1 millimeter each. I have at home. I have with me a system with 1 millimeter prisms built with the projection microstereolithography, and so that is not easy. It takes a long time to build this large number of units, but theoretically the behaviors are scalable. So all you need is a sufficient number of units. There is no influence of the scale of the assuming it is not dramatically small.
But you'll also need a very high Q factor if you want to observe this phenomena over hundreds of cells. Then
that's true.
It's better have good Q factor. So if this was
Yeah, that's true. That's true. That's true.
So with the strings, I saw plastic strings you use in one experiment. Those I think will not give you the
No plastic. We are
to-
using the spectral strings. Our favorite strings. Yeah. If you go, okay, but these are for the the large scale system. For the small scale, you're right. You're right. The plastic system strings will not help. You're right. That's true. That's true. That's one of the reasons. You have a lot of damping. You have a lot of energy dissipation. There are other phenomena, viscosity. Yes, you're right.
And so, speaking of which, sorry, Emile, speaking of which, you would not see this in real, natural, large-scale structures.
Yeah, it's a challenge to build. We hope that the research will find a way to build the real tensegrity systems. In the end, nature builds tensegrity systems, so we hope to be good enough to imitate.
But with respect to to the point
the
raised
cells,
by Emile.
the cells. Maybe we have to look at collections of cells. The cells are tensegrity, so can be described as a tensegrity. So
maybe Martin has a word here because he built this very high Q resonator.
No, I actually had a completely different question. So should I or should I not?
Sure.
Yeah.
I would like to understand better the connection between the solitary waves you are talking about here in mechanics and the solitary waves I know from optics. You mentioned that some of these waves are super sonic that you are considering, whereas in optics, as far as I know, the wave is always luminal. So why is it that they become supersonic and not superluminal in optics? There's something I do not understand.
I think that it depends on the regime of excitation of the system, most probably. The regime that we have been exploring is this one. Maybe there could be regimes, yes.
Maybe this is just a speculation. In optics, one is always discussing very small perturbations to the refractive index or to the polarization, whatever you want. Whereas in your case, I think you have pretty large nonlinearities.
Yes,
is that in the language of optics, you are going outside of the perturbative regime?
All right, yeah. This is something I'm learning. It's nice. Yeah, we have a large nonlinearity. Yes, that's definitely true. This is you have seen that basically we had the 30% axial strain in the strings of the systems that I showed. 30%, so it's very large. It's a finite deformation of the system. Of the strings.
But then also the equations of motion that you are considering and that one typically considers in optics must be different, right?
Yeah, could be. I'm a mechanician, so from my point of view, the equations of motion I'm considering are correct as long as you have point masses. If you have point masses, you can describe the mechanics through the equations that we are employing. So
this is not quite what I mean. I mean, in optics, people are usually mapping solitons or solitary waves onto the nonlinear Schrödinger equation, as they call it.
Yes.
Is this the same for you here?
It's I don't know about this. The theory of solitary waves we are referring to is that of discrete particular system with nonlinear interactions, which have a wave equation which is named the Netherenko wave equation, and is particularly nonlinear and shows solitons as a solution. So our theory, the reference theory, is that of the Netherenko book on nonlinear particulate systems with a system of mass spring systems with the nonlinear interactions. So that's the math that is underlying these systems.
I must admit that I do not know anything about this equation, but probably I should.
I don't know very much about the equations that you are more you are a physicist, I understand.
But you know, Fernando, the equations that Martin mentions, I think they are the equations used for solitary waves in fluids.
In fluids, yes.
Yeah, the NHS, you know, nonlinear Schrödinger equation, I think, you know, in 1D.
Yes,
No?
which
Maybe,
is
maybe Emil, you could comment on that. Maybe you know more, no?
Can you repeat?
Yeah, what would be the typical equation you use for solitary waves in fluids? It would be nonlinear Schrödinger equation as well, no? That's what we
So
could
the
use
way,
as well.
yeah, the way I will approach this will be through Liouville equation.
Okay.
So in that case, you even for large deformations, when you go through Liouvillean, it linearizes the Hamilton equations, and it becomes again a linearized equation, and then you can again think of eigenvalues, eigenvectors. So this is how I will look at this thing, and this is why I ask about excitations.
KdV equations are evolved towards the Nesterenko wave equation when the nonlinearity is high. So the Nesterenko wave equation refers to a medium without tensile strength. So those are referred to as a sonic vacuum, sonic vacua. So mediums that have only media that have only compression strength, and so in this media you have this the wave equation is that ruled by this equation that has been shown by Nesterenko for mass spring systems with the strings that have a power law equation with the power law exponent that changes from greater than 1 to lower than 1, and he has shown this solitary wave solution. That's all I know. In other branches of physics, and I'm not an expert of the mathematics of solitary waves, we have only found those results. The mathematical proofs only refer to the fact that we have been relating our work to in one paper, in one unique study. All the other studies have been only numeric. In one paper, we have compared the potential of our system to that has been shown by Frisike and Pego to support solitary waves through mathematical arguments. So I'm not an expert of the mathematics of, I know that it's a field of intensive research. I'm not an expert about the mathematics of solitary waves. And that's why, since I know that mathematicians and physicists always ask me, are these real solitary waves or not? And I'm not able to answer the question rigorously. That's why I name the waves that I've been describing as compact compression waves, not necessarily solitary waves. So we are investigating about for example, the energy that is the variation of energy after impacts to numerically investigate about the properties of the waves, but we have no mathematical theory of this system of the wave phenomenon that we are analyzing. So I cannot be able to prove mathematically that those are real solitary waves. Only in one case, in the rigid elastic case, we were able to prove that those are solitary waves, but because we connected, we demonstrated that our system had same properties that were shown to be the right one to support solitary waves in a mathematical study. But our study is more numerical, and so actually we have to use solitary waves in a cautious way. I think they are solitary waves, but I cannot demonstrate mathematically.
In the talk we had on the nonlinear systems, was it 3 weeks ago?
Vincent Tournat?
Yes, the soliton solutions depended crucially on the bistability of the system, which here doesn't. I think we are far away from the bistable, from that point.
No, it depends only on this geometric effect, the large deformation effect. It doesn't come from bistability. There are solitary waves also in bistable systems, and these are more simple to investigate actually from the physical point of view. But this is only shown in one of the simulations that I have been illustrating. That all the other ones, in all the other simulations, the origin of the solitary waves is not bistability, it's not stability.
Yeah.
We are far away from the stability. The system is stable, but there is this stiffness that increases or decreases with the displacement. That's the only source of nonlinearity that is behind most of the results, almost all the results that I have shown. The bistability is different. It's different.
Can I ask if the velocity of this the supersonic speed, does it depend on the length of the system? Because it looks like this compact wave feels like
yes, it depends. It depends on the sound speed. So the sound speed, yes, depends on the length of the system.
On the length, as you take the length larger and larger, I guess it's no longer supersonic, because it looks like this excitation feels like the stress has been increased locally or something.
But you can always impact with a sufficient large velocity in order to reach this supersonic regime. You're right. That's true. But you need to change the impact velocity in order to excitate this supersonic regime. And obviously this will be difficult from the physical point of view, because it will break the system very easily. Yeah.
In the very first slide, you show the silk of a spider. It's very striking when you look at that picture, because you see connections at different scales, and how this spider can achieve that. It's the very first.
I'm mentioning in words.
Here,
it works. And I have been actually running. I have a publication on the tensegrity modeling of the spider silk. In that case, it depends. There is one interpretation by Skelton. Bob Skelton has been my mentor for tensegrity structures. That in the spider silk, there are these beta sheets, that is proteins that are provide a compressive stiffness to the system. So you have a bunch of amorphous strands which are connected by these beta sheet plates that can be regarded as compressive members. And so this net of strands has an increase in the stiffness because of these compressive members. Because if you have a net of tensile, if you have only longitudinal fibers without connection, without compressive members connecting those fibers, you get a lower axial stiffness than in a network of strands connected by those compressive members. So this tensegrity modeling of the spider silk comes from the assumption that you have as in all the tensegrity, you have a sea of tensile members in connecting compressive members, which are the beta sheet plates.
Yes, and here, as you can see, there is a connection at different scales. If I look at one point, then I see first nearest neighbors, then it's further near neighbors. So it's that almost gives like a uniform response in frequency, I will say, when you see that kind of
Yeah, I think
connection.
so too. I think so too. If there are large scale interactions, that I think this we have not we have not
So-
analyzed that phenomenon. But yeah, long scale interaction can alter the response. Yes,
Yeah, so
definitely.
here it's a multi-scale, because at each scale you will see connection, at least in the second picture that you see here.
I don't know which one you refer, but
Yeah, just the second column, on
the solid one. Yeah. Okay.
on the slide.
Yes. Yeah. Indeed. This is the fractal. Yeah, actually, yeah, you're right.
That's right. So this fractal should show scale.
You're right. Okay.
In
You're
space
right.
and frequency.
You're right. This is another challenging figure. You can build tensegrity fractals by, this is through the self-similarity rule, by subdividing recursively the units. And so, yeah, you're right. Yeah, I didn't realize you were referring to that. Yeah, you're right. You have here like long range interaction. So yeah, you're right. You're perfectly right. Yes, you're right. Nice interpretation of this figure I had never thought about, but this is true. This is actually true. Thank you. I mean,
Well, thank
for
you.
this
Thank you for
insight, in this insight, yeah, which
For that.
opens also different areas of possible research.
And could we go back to this solitary wave when you have more than one dimension?
More than one, yeah.
Yeah.
Obviously, we see only the motion of the system in this.
Yeah.
Okay, but okay.
So
what will happen if you hit again fast when you have the left end thermalized? Will you be able to excite?
Yeah, you always have this. You can, if you repeat, I'm not sure. We run this simulation, Emil, so I don't want to be to say anything wrong. I think it will maybe happen the same. The same will happen because this
Even
is
even if the end is thermalized.
yes. I'm not sure. I mean, I didn't run this
Yeah.
simulation, so I don't want to argue anything wrong.
This is almost like firing two bullets one after the other.
You're right.
One first bullet will do damage, but if the second one cannot, that will be something to think
You're
about.
right. You're right, but those are fractions of seconds. So for the applications we were thinking about, it was not important. But you're right. Indeed, we just published one paper on this study. I think there is a lot of research to be done, both numerically, theoretically, and experimentally. There are a lot of things to investigate on. So far, what I can say is that tensegrity systems are toy structures which allow you to do several things, but this is not easy to reproduce in real life at a small scale. At a large scale can be done, but at the small scale for metamaterials is a challenge. Is a challenge. There are people investigating. There are researchers. When I started, no one was studying tensegrity systems in this area, but now I see that there are a few people working on tensegrity systems as metamaterials, and so maybe we will find also we'll find a way to build. One of the main goals of Bob Skelton was to build a machine to build tensegrities. He never succeeded in that. He had this idea for many years of building like a sewing machine. That was his idea, but he never succeeded in depositing the patent. Yes, and that's a challenge. That's a challenge for the large-scale application. Anyway, for scientists are nice structures. We are also, I don't know if you know, but I also have a company which makes tensegrity lamps as a furnitures.
Oh, you have a company?
I think this will be more successful. Can be more successful. We are building a tensegrity lamps also, which are
Interest, Oliver, I think.
yeah, which are actually are nice. They look nice, and so
well, these are wonderful ideas. If you think about this thing, the fidget spinner, you cannot believe how, I don't know, how many of these were sold, and any of these ideas can be made and actually then commercialized.
Yeah, and actually we think that since architects like tensegrity, I have my own idea why they like tensegrity anyway. The main reason is that they don't like bending. So tensegrity structures are good because they do not show bending. That's one of the reasons. And also the structures, there are artists. There is an artist, Kenneth Nelson, who has worked mostly on tensegrity. So I think that for science, they are nice structures, toy structures. It's difficult to build small-scale systems, but definitely as a furniture or as a interior design systems, they have a potential. Yeah.
I would love to have one just to press it and see what it does. I will buy one for
but Emil, the point is that in order to be successful, you need to sell these systems to people who are not scientists. I think they were very popular among scientists. I'm not sure they will be.
I think this is an example. Just you rotate and you look at it. And
yes. Well, I like many metamaterials. I think that many metamaterials can be nice objects for also other metamaterials. The chiral lattices or other metamaterials can be nice as artworks, as interior design furnitures, maybe, or panels, or something shading panels or something like that, like measure via some lattices. So this is true for many materials. But we are investigating. I don't know, Bogdan, if I have 1 second, I want to show these lamps. This is funny.
Yeah.
Yes. Can I run an external website?
Because I think Oliver also showed us wonderful things. Oliver.
I think if I share my screen and if I run the website.
You just have to open it, the website.
Yes.
We'll see it.
So it's MetaMAT is the name of the company that I incorporated in the University of Salerno. It's actually a spin-off of the University of Salerno. It's approved by the University of Salerno. And this is the website. And this is a tube lamp. But what I want to show you is this flower lamp that these are kinds of lamp. So this one is the flower lamp. This is a flower lamp, which is a tensegrity structure.
Wonderful.
And is activated by this is entirely 3D printed. It has some eyes which are opened and closed by shape memory alloy wires. So the idea is that when you turn on the light, the Shapery memorial laws, when you reduce the temperature, when you increase the temperature, they will contract. And so the idea was to by turning on the light, you will contract these wires, and you will open the eyes. And then when you turn the light off, you
Eyes will close.
you close the eyes.
Wow, nice idea.
And this is the lamp. These are several.
Wow, that's amazing.
I have in my lab, and yeah, this is in a showroom. But anyway, this is what happens.
Oh, wow. Wow.
Yeah, we have been working several months for this.
So you should sell this also, for kids.
Yeah, well, I cannot sell it, Sebastian, because you don't have the authorization.
No.
It's just one piece. You cannot do it in an industrial way.
No.
For you need a certification.
Yeah.
This was for a competition. So we are doing something more easy for selling the lamps, and we have actually a simpler lamp built with designed with this is more simple. We are working on this this one. This is also tensegrity. This can be sold. This can be sold. Maybe
Yeah, but it's less impressive. It is less impressive. The other one is really more impressive. This one, okay.
For your table, I have one in my office. I think this is cool for the table of a scientist.
Yeah, okay.
Not only. I think many people enjoy.
I'm sure that Oliver would like to show his website then for comparison with his. Oliver, can you show us your website with your lamp?
So you have a lamp.
Again? You want to see it again?
Of course, please do.
No, show the lamp, absolutely.
Show the lamp, oh my goodness. Sure thing. Wait.
It's a lamp competition now on
It is a lamp competition now.
It's a good one. It's a good
Become
one.
a lamp competition.
Light competition, yeah, true.
No, it's a fantastic website. I really like your website, Fernando. But Oliver has a very nice website as well.
Okay.
Is this what you mean? Can you see that?
Look at this. Look at this, Fernando.
I'm not jealous. So show me your website. Wow. Those are.
This is what.
Desk light. So, so we should talk.
Definitely. This is
you have to acknowledge MetaMAT. You have to acknowledge MetaMAT, guys.
A shock.
We should run
competition.
Glow wide.
Look at this, Fernando. Look at that.
Wow. It is cool, indeed. It is cool.
Cool stuff as well.
Yeah, it's cool. This is
still in Italy, but the Italians are very, very proud of their lights. They have fantastic lights.
No, we have we can add the Italian touch.
A tensile touch.
No, the problem is I have to admit that I don't know, Oliver, about you, but with my firm, I had to hire at a certain point an architect, because you need an architect to make things cool, to make things that look sexy for the people to buy. I don't know. How does it work, Oliver?
Well, this one has. Let me. Got to try and.
You know that we can make it bistable.
Yeah, this works by
bistable. I'm not joking.
This works like the light comes inside the guide and then it's refracted from the edge like that.
Wow.
Yeah. So it's a waveguide. It's waveguide.
How much does it cost, Oliver?
In Europe, it costs 290 euros. It's quite a lot.
But who fabricates this product?
Me. Yeah.
Can you do that? Can you do that? Do you have authorization for? Yeah, because no.
Well, it's my company, but it's like
Wow.
I'm not an employee. I'm just an owner, sort of thing.
I know.
I know.
I know because I
Really?
do the same. So I do the same. So.
Okay.
But most probably you make more money than me. Yeah.
No, well, it's just managed to sort of not lose too
I
much.
don't make any money, so for sure you make more money than me because so far I have sold to my mother. My mother wanted one lamp. And we just
Well, you know, this is
just
how
started.
Rockefeller started. You know, Rockefeller started very little and then
Yeah. Yes, we always hope to do better and better. So far, so
This one.
Oliver, when I send you this information about this experiment, you please send me the link of your company because it's very nice. Actually, I like it. But
Yeah.
this is kind of wow. I see. So you can change the orientation.
It goes like inside like that.
No, the point is to spread the light over a cone.
Molto bella.
It's
Very,
a rectangular
very nice.
area, yeah.
It's very nice.
So
Bellissimo, sì. It's very nice, Oliver.
now this cone is always fixed. It will be nice to have it adjustable.
Make it top style.
Yeah, maybe with a tensegrity system we could adjust it, perhaps.
So if you have the cable, and you stretch the cable, you can vary the cone. I see.
It should be very simple.
But this is it's very nice, Oliver. Very, very nice, actually.
Look, guys, we were talking of solitary waves 10 minutes ago, and now it's a lamp competition. That's wonderful. I like it.
Wonderful. My idea to show you the light.
It is nice that there are
it's great. It's great.
It is nice that there are other people who share this. My father was an architect, so I have in my chromosomes, I have some attraction to beauty, to architecture, to beauty, and so that's why I have this. I started this.
Fernando, do you know the museum in Marseille? Museum.
No,
Bogdan, can you show the website so that he sees the architecture of museum?
A second.
It's a fantastic building. It's on.
It's very nice. So you have different supports. I see. You have the snowflake. What is the snowflake about?
Snowflake, because I'm from Hokkaido, so it's like today it snowed 40 centimeters. So it wouldn't be fun without a light that was based on snow. So
I see.
The snowflake is the same thing, but with
small holes. This is. I want this one. Because my girlfriend loves the snowflake.
This light is from Roma. My friend in Roma from La Sapienza is stocking them for me.
Who is this guy?
He's a thermal physicist called Roberto Livotti.
Okay.
Professor Roberto Livotti from what's it called now? Anyway, Energetica it used to be called. Yeah.
Oh, but this is beautiful. The snowflake interior stand light. This is beautiful. I have to. Wow. I'm jealous. I want to do something.
Snowflake. There's a snowflake in stock.
This will project. Basically, this will project snowflakes on the desk. This will give some patterns.
I don't think it's. I think you're reading too much into this. It just looks like what it looks like. It doesn't really project.
Okay. But I'm pretty sure it will also produce some patterns of light. Some
snowflake. Lots of people buy it for their kids in
I know.
Europe.
There's also
People seem to want to buy it for their children. I don't know why. For their children's bedroom.
Okay.
It's lovely. It's really lovely. Tu as le site web du MUSEM, Bogdan?
I can share it.
Yeah, Bogdan can show you something which is quite amazing in terms of architecture.
I should also mention that some people like the industrial feel rather than the slick feel.
Mm-hmm.
Bogdan, you need full screen so that people can see the
anyway, Oliver,
pattern.
we should talk because
don't worry, I was going to write to you after
we can
this.
do things together, I suppose.
Don't worry, I'll be in touch.
Oh, this is this facade.
And it's concrete. It's concrete. This is really the structure of the building. This is the structure of the building.
With optical fibers. I know about this project. It's pretty cool.
Yeah, it's
pretty cool.
Yeah.
Wow.
It's quite amazing, this building. But perhaps, Bogdan, you want to show it in full daylight because
SAM is for cement, probably. Oh no.
It's a museum.
Yeah, but it is just a double meaning word, probably.
Yeah, sure.
So Bogdan, can you show it in daylight?
Yes, daylight would be better, Bogdan. Just full daylight without this. Christmas lights.
Sorry, I lost.
We don't need this. We just need to see the structure.
So it's interesting when you pattern a surface, then the surface can look very different from different angles.
But here, it's the facade. It's not only the surface; it's the facade. This is the structure of the building. It's
a facade. It's a facade. Yeah. This is very cool.
Yeah.
Very cool. You have to admit.
And it's lots of engineering, to have such a structure which is robust enough. Look at the structure from this,
Yes.
All the structure. Il nous le faut en full screen, Bogdan. Il voit pas la. Voilà.
Yeah, this is like a pattern. This is a lattice.
Sorry, my connection is not very.
Yeah.
Can you see it here, the entire building?
Yeah.
The entire building is like
but I have seen that the facade made of this pattern, which is very cool.
Yeah.
Wow. This is, I think it's inspired from the bone.
If you look at my lamp has also this pattern. It's just a pattern. So these patterns are cool for creating effects, light effects.
But also the air circulation is very good, you see, because it's on the seaside, so you get, the sea breeze and so on. This is totally amazing. This building, it's totally amazing. Yeah,
beautiful.
It's quite unique in France.
I like people from Marseille, but I have never been there. So I like people from Marseille because look like Neapolitans. So you have similar attitudes. So I have to go there. Sooner or later, I have to go there.
I don't know if it's a coincidence, but this building's pattern is the same as your lampshade, isn't it?
Yeah, that's
really reminiscent. Yeah.
There is some similarity. Yeah.
Mm.
Actually, we were inspired by the patterns, the conjugate to Delaunay triangulation, the dual of the Delaunay triangulations, which are the Voronoi pattern. So we create a Voronoi pattern, and so for the lamp, which is similar to what has been done in this facade, which is very, very cool.
And in fact, it's an engineering company in Toulon. They really needed to design a very specific type of concrete for this. It's really a lot of work to.
Not a lot of work. I understand, because this is not solid concrete. It's not massive. You have those members. I think nowadays there is is becoming more and more popular, the 3D printing of concrete. I think this could be one of, but it's beautiful.
Yeah.
It's absolutely.
So it's
for how long has been active this museum?
Can you repeat, please?
When did it start? When did it start?
I think it's 2013. It's very recent.
I'm a bit ignorant, I have to admit.
And
this is at night. This is a night.
No, it's a day. You can walk into the walls around the building.
Around the building, yes.
You have a corridor. You have a corridor on the facade,
I see.
and you feel the sea breeze when you walk down the corridor. And you can see also you have a flyover, from the fort to this museum, and it's totally unique, and it's really in the city center.
Marseille.
Yeah.
This is one of the most beautiful terraces of the.
You see the patterns. Yeah, you see the patterns. Yeah.
And it's a museum for the Mediterranean civilization. So really,
it also reminds me of this Arabesque
in
the Masharabia.
Totally.
In France, you have the several examples. Also in Paris, of this Masharabia facades. So it's also this is another area of research.
Look at the sky view now. You see the flyover. So you have the fortress. It's a fort. So this is Fort Saint-Jean. And then you walk on the flyover and you end up on the terrace of the museum.
I see.
You go down the corridor and then you can
there's a bridge. There's a bridge.
Yeah, it's just a bridge, but it's just for for people walking. It's just like a flyover.
Bridge. Yeah,
very tiny, and the view is really stunning because you have the islands and so on. It's
very interesting here next to this the museum this building which is called Villa Mediterranee have some floors under the sea, have some amphitheater, cinemas,
like an aquarium.
The roof.
What I love of France is that you are so brave to build modern structures close to the very nice, beautiful, close to ancient structures. In Italy, there is no modernity. It's not possible to build anything modern in an Italian city because it seems that it offends the history and so. But while I think this new architecture can be integrated with the old architecture, as in this museum. So, like in the Grand Arch in Paris, you have the pyramid and the Louvre. You are more brave. You have more courageous people, and I think this is successful. It's rewarding. It's beautiful. So
this pattern, by the way, is not entirely only from the Western world. The Japanese historical lights also have this pattern. I've just realized. Would you like to see
oh yeah, of course.
Sure,
Japanese lantern based on this, roughly on this pattern?
I see this.
This is a Japanese lantern. It's a little bit like it, isn't it?
And this is is modern or is traditional?
This is antique, an antique lantern. And you can see on the...
Because nowadays, these are very popular.
It's making nice shadows on the snow outside. Can you see that?
That's why we build that pattern, because we know that nowadays those lamps are very popular. And so those are done on purpose. But this is true also in the... You can build... okay, yes.
Quite the same, though.
But Oliver is saying that could have been made 1,000 years ago, maybe.
Yes.
It's a little bit different, the pattern, though, but similar.
Yeah, it's
I better
similar.
shut the window. It's cold outside.
The pattern can be different types, obviously, different geometry, but the idea is the same. But in that case, it's the concrete with optical fibers, if I I'm right. That gives this fascinating, the large scale, this fascinating effect.
Line appeared.
Which says,
That's a day. That's a year.
Great.
Is it check?
So I think there are also some students now have seen that the scientists also have this artistic interest, which is interesting. Bene.
no. Yes, I used to say that, okay, with the scientists, we just take the ordinary matter and make it behave in extraordinary ways
Yeah.
by just engineering couplings and connections. But at the end, it's just ordinary matter, which you wouldn't say. By the way, if you are...
You also have something to show. Okay.
Yeah.
What do you have?
This is the coin. So this is like a enlarged version of a coin.
Yes.
Now they sell it saying that this is the Euler disc or Euler disc. And here is what it does. It goes forever.
Oh.
So I got this one for $37, and my daughter loves it. And you can put different colors on top. But the interesting thing is it just goes. It goes for a few minutes.
Wow.
Wow.
And of course, you know this phenomena when you toss a coin here, but the coin will die out maybe in 30 seconds, while this one, you will see, it goes on and on. And people think that there is some sort of a driver inside, but it's not. It's just gravity.
What material is that?
So it has to be steel, and this one is also steel, the mirror. So that's the main. And if you put a finger on the table, you can see how the energy dissipates. So if I will have a more sturdier desk, this will last much longer.
Okay. Okay.
So Emil, you've got a
Yes.
website for us to buy this kind of stuff?
No, this one you find it on Amazon, and there is all these gadgets come from the same company, which I think is from Japan.
Oh.
And they sell the usual collision experiments, and they are all sort of desk gadgets for
Wow.
people.
So we close the loop. We are back in Japan.
But
I recommend the YouTube video of Tadashi Tokieda, the Cambridge University Japanese mathematician, who explains this exact toy, how the period of vibration goes as the cube, the third root of time as it approaches the stopping point. It's like some kind of phase transition type theories. But he gives fantastic talks on toys, this guy.
Okay. So we should have him in MetaMAT. We should invite him.
Invite him.
Yeah, totally. I'm all for it. We should invite him. Yeah.
He's used to talking to audiences and keeping them so happy with his fantastic talks. Really unbelievable.
Oliver, could you put us in touch with him? Is it possible for you to put us in touch with him?
Okay.
Yeah.
I'm not sure.
It's not like he's my friend, but I'll get in touch with him and tell him about it.
Yeah.
I'm not sure if you see the next level of this thing.
Oh.
Give us a talk about toys. Yeah, that would be nice.
Okay.
I'll get back to you on that.
Okay.
Okay, thanks, Oliver. Thanks again to Fernando.
Thank you.
It was very nice. It was very nice
Very
meeting you. It was very nice meeting you, and I look forward to other meeting occasions.
Of course.
Yeah.
Thank you
Hopefully
for
in person.
explaining
Hopefully
us,
in person.
and of course to for bringing the tensegrity into our community. Thanks, Emil. Thanks, Martin is not anymore with us. Sebastian and Oliver for your questions and your toys, ideas. And
lamps. I love the lamp. I love the lamps by Oliver.
The lamp. That was a nice twist.
I love the work by Oliver. Yes. Congratulations, Oliver.
We promised it in the past, but we should definitely do it. I think with your agreement, Fernando and Oliver, of course, we can have some links to your companies, you know, if that's okay with you.
Yeah, we
can
just
put it on our
started.
website.
Oliver is more solid. We just started, but we have ideas. We have ideas.
No, but,
Okay.
you know.
Don't want to be mistaken for a commercial guy, you know.
No. It's just, you know, we can.
I just waste the money in my company, but it's I enjoy
just,
it.
you know, it's really cool stuff. I mean, it's not just, you know, boring science. We want to do a fun science. This is fun science. Yeah.
Maybe scientists or kids may be interested to
exactly. Some
yes.
perhaps ideas for outreach for teachers.
Okay.
Okay. Thank you all, and see you next week. We will have Professor Zhengai Hu from aeronautics, aerospace engineering, actually, in Beijing, and he will talk about elastic metamaterials and their application to wave control. So thanks again, and see you.
Grazie, ciao. Ciao.
Bye.
Thank you.
Bye.
Thank you, everybody.
Arrivederci.